When I first started this chapter talking about bonding, I introduced the concept of ionic bonds where the electron is transferred and covalent bonds where the electron is shared. Now we're going to talk a little more about shared electrons because they're not always shared evenly. We have something called electronegativity, which is the relative ability of an atom in a molecule to attract the shared electron. So if you have one atom that has a high electronegativity, it will attract the shared electron more. And that will result in the more electronegative atom having a partial negative charge. And we call that polarity. Polarity results from an uneven partial charge distribution. The molecule has positive parts and negative parts. Now, Linus Pauling gave us these electronegativity numbers. And the way he did this is he started with fluorine, which is our most electronegative atom, and he gave it the number 4. Then he rated all the other elements based on their comparison with fluorine. We can use the periodic table and we can use Linus Pauling's number to arrange the atoms in increasing electronegativity. So if we have lithium, sodium, and potassium, we see that these are all in a column and that the electronegativity decreases as we go down the column. So the one with the, let's see, we're supposed to be going in increasing, so we want the least, oh, I did rubidium instead, sorry. So we'd start with rubidium or potassium, would have the least electronegativity, then sodium, and then lithium. If we look at a row, we could look at sodium, chlorine, and potassium. And we would see that as we go across a row, it increases. So sodium would have the least in this group, and then phosphorus, and finally chlorine. For this last grouping, we've got silicon, calcium, and oxygen. They're not in a in a row or column, but kind of go across. We've got silicon right here, calcium here, and oxygen. We can see that as we go, that let's see, calcium is 1, oxygen is 3.5. Make sure you can see it. 3.5, and silicon is 2.5. So calcium has the least electronegativity, then silicon, and then oxygen has the most. We can also, without the numbers, just remember that fluorine is the most electronegative, and so as you move away from fluorine, either across a row or down a column, the electronegativity will get less. Okay, to calculate an electronegativity difference, we just look at the electronegativity numbers and subtract them and take an absolute value. We don't care whether we get a negative or a positive number. We're just looking at the absolute difference in the two numbers. So let's look at some examples. And what electronegativity can tell us. If we determine that the electronegativity difference between two atoms is 0 to 0.4, this is a nonpolar covalent compound. And we're going to say that the electron is shared evenly. That this is such a small electronegativity difference that the electron is shared evenly. And it would look something like this. If this was one nucleus and this was the other nucleus, we'd have the electron spending about the same amount of time in both. The diagram's not great, but those are supposed to look like even halves. If the electronegativity difference between two atoms is greater than 0.4, but not greater than 1.8, then we have a polar covalent molecule, a bond. And here, the electron is still shared. It's between the two atoms, but it's shared unevenly. And if this is one nucleus and this is the other nucleus, we might get something that looks like, I'm going to draw a bigger circle on this side. My artwork leaves something to be desired. And we get a partial charge. On this side, we get a partial negative charge because the electron is spending more time on this side. And on the other side, we get a partial positive charge. Note that the nonpolar covalent, I didn't draw any charges on that because it's shared evenly. If the electronegativity difference is greater than 1.8, we get an ionic bond, and the electron is transferred. And we get something that looks like this. This is one nucleus, and it's got a positive charge, not a partial positive charge, but a positive charge. And this is the other one, and it's got a negative charge. So we've made an anion and a cation. So we can use the numbers from Linus Pauling to figure out whether these bonds are polar, covalent, ionic, or nonpolar covalent. All right, so silicon is right here. It's 1.8. And bromine is here at 2.8. So the difference in those is 1, and that puts us in the polar covalent. And I guess I'll write well. If we look at bismuth and fluorine, I'm going to have to move this up because bismuth is all the way down here at 1.9. And we know that fluorine is 4. That gives us a difference of 2.1. And we have a difference of 2.1. That's greater than 1.8, so we have an ionic bond here. It's actually a bond as well. Okay. Let's look at bromine and fluorine. Bromine is this 2.8, and fluorine is 4. So we get 2.8 minus 4. Notice I'm not paying any attention to my signs. These are all absolute values. 1.2. And that makes another polar covalent bond. Okay, let's do the iodine. Well, iodine is 2.5 minus 2.5 gives us 0. So this is a nonpolar. And I could have done that actually without looking up the numbers because number subtracted from itself would always give you 0. Okay. Now, sometimes it's useful to know actually where the negative and positive charges are. So a dipole moment results from a separation of charge, and all our polar bonds are going to have dipoles. So let's see how we would write these dipoles on our diagrams. If we have a bond between nitrogen and fluorine, we can look on the periodic, on our little cheat sheet here. Nitrogen is 3, fluorine is 4. So fluorine has a higher electronegativity, and so we would expect it to have a partial charge. So we could write this as partial negative charge on the fluorine, partial positive charge on the nitrogen. And I know that because nitrogen has an electronegativity of 3 compared to fluorine's electronegativity of 4. Now, it's kind of messy drawing these partial charges, so there's a shortcut for drawing dipoles. You just draw an arrow, and our arrow, I'm going to give you the color for our arrows. Our arrows are going to put the positive, gets the arrowhead, and just to remind us that the tail is positive, we put a line there. So that looks a little bit like a plus sign, and the plus sign goes over the partial positive atom. So we would draw this like this. So we look at bromine and silicon on our over here. Bromine is 2.8. Silicon is less at 1.8. So we would draw our dipole like this. Silicon's going to have a partial positive charge, and bromine's going to have a partial negative charge. If we do oxygen and carbon, oxygen is 3.5, carbon is 2.5, so the oxygen has a greater electronegativity, a greater affinity for the electron, and so the electron is going to hang around the oxygen, leaving the carbon partially positive. Okay, so in the next video we're going to talk about how molecular shapes are made.